Thank you very much once again, Krishna, for giving me this opportunity. And this opportunity is much more important because at this juncture of my career, I wanted to interact with researchers and to get the ideas where I should be heading, to be very frank. So the title which I have chosen is Expanding the Realm of Environmental Geotechnology, the Limitations and Possibilities. This is a state of, introspection, you may say, where we would like to realize as a professional where we are heading to, having done so much. You are a pioneer in the subject of environmental geotechnology. There have been many colleagues who have contributed significantly. And now, looking at the present day circumstances, it becomes very important to have this type of introspection, that where the subject should be moving to, what should be done to make it much more, universal, more visible, and much more powerful. So I am DN Singh, as he said. I work at IIT Bombay as a professor, and I would like to now start my presentation. See, this title, the EnV GEOS, has come to mind for those who have been associated with me, is my collaborators, research collaborators. They are my students, they are my colleagues, fellow researchers, funding agencies. So this is the tag which I have given to all those who have worked with me in any capacity, and the evaluators, examiners of the thesis, referees, journal editors, whatever. The way I feel, this is our profession is like savior from of sins. We save the mankind from whatever sins have been committed. And we also preach that why sins should not be committed. That is what actually our main motto is. Very similar to the surgeons, to whom the patients go at a very critical stage. And very likely, the situations could be individualistic, site specific, location specific, problem specific, and there could be needs specific also. This needs based thing prompted me to write my book, which I'll be discussing about later. So what is the genesis of the entire story? The story is like excessive, selfish, greedy, and lackadaisical exploitation and consumption of natural resources has really brought us to this level, where we are bothered about the sins and who is going to clean up and who is going to pardon us and who is going to be the savior. Most of these accidents which have happened in the past, mostly because of unscientific disposal and storage of effluents. Effluents are the bad products which are coming out of the industries. They could be in the form of sludge, liquids, they could be solids also. So I classify them as byproducts. Byproducts are the ones which are bad products coming out of the industry, which are not intentionally generated or produced. Mostly these type of byproducts are radio, chemical, biological in nature in general. And they are basically interacting with the geomicrobiosphere. Geomicrobiosphere is a bigger term, which I have discussed at some other places also. It basically talks about the entire ecosystem by giving proper weightage to the microbial activities, which harp into the geo-environmental space. And when I say geo-environmental space, it's basically the subsurface, where we have soils, we have rocks, where we have groundwater, and these are the major constituents. So I'm sure most of you must be aware about Reddy's Krishna's lecture 2013, where he has talked about the left canal, Niagara Falls landfill for chemical disposal. He has also discussed in details about the Valley of Drums, Kentucky, where a site with toxic waste drums were created. In the not very recent times, but in the past, the Chernobyl nuclear accident which occurred. This was a disaster, and this list actually goes on and on. And I don't think this is going to be a list which is going to be ever ending. So this is a never ending list. Now, these type of disasters, they forced mankind to create RCRA, that is Resource Conservation Recovery Act, and Superfund laws and other things. So from this point onwards, the major emphasis was on waste containment and soil remediation. Most of the researchers have worked in this area. Now, what I'm going to do is I'm going to take you through the evolution of the subject as it occurred, starting from the waste containment facilities and the soil remediation after these accidents took over. So the first job which people did is that after the accident took place, the soil remediation through chemical processes was conducted. This also led to the design of engineered disposal facilities, containment facilities, be it the landfills, be it the toxic waste disposal facilities, be it some industrial waste, radioactive waste, and so on. And this is where the contaminant-geomaterial interaction was studied by the researchers quite in details. And still people are studying this. This is where the deep disposal of radioactive waste also came in picture. And many of us have worked in this area. And we have tried to create the facilities which are going to be safe for disposal of toxic waste, which is of radioactive nature. Now, when you talk about the contaminant geomaterial interactions, these are the typical situations which come across in our mind. There is a water table, and the waste is being contained in a capsule or in a canister. And then this is most of the time when we talk about the nuclear waste, we use lead shielding and so on. And ultimately, this system is buried in a compacted geomaterial. And then we say this is the safe isolation of the waste from the geoenvironment. This is what is also known as surface disposal. There could be another situation where the disposal of the waste is done deep inside the ground, up to about 10 to 20 meters. This is depending upon the intensity of the waste. This is very low intensity waste, or maybe medium intensity waste, low level waste they call it. So where the engineered backfills are created, and depending upon the water table, these type of systems have to be designed so that nothing leaches out, nothing comes out in the geoenvironment because of the fluctuation of the water table. This is what is known as near surface disposal. Some of my PhD scholars have worked on both these systems, and we also studied at two different places in the country, in India, where the high level nuclear waste was disposed in the deep repositories. When we say deep repositories, these repositories tend from approximately hundreds of meters to maybe less than 1,000 of meters, where the backfills are designed of different types of minerals and the soils, and so that they remain cut off, these units remain cut off from the geoenvironment. But the major issue is, fluctuation of water table, or in case of any sort of, in extreme conditions, the corrosion of these units might occur. And once the corrosion occurs, the toxicity might leach out. And this becomes a very, very difficult situation to handle. So most of the time when the waste disposal facilities are being created, several issues are kept in mind. So some of these issues are that which lead to very good R&D. Actually, before this seminar started, I got some emails, and people requested me to emphasize more on what could be the research opportunities. And I have included them intentionally over here. Please feel free to stop me in between and discuss or interact if you wish to. Otherwise, you can write down the question, and as Krishna said, we can take these questions after I finish my talk. So some of the opportunities for R&D would be site selection itself. Site selection, that means to identify what is the candidate repository. Repository is a geological formation which is intact, and under no circumstances any waste material which is going to be disposed of here should go out. So you can characterize these type of systems, geological systems, and make sure that no activity is going to become a part of the geoenvironment. The second is selection of the geomaterials, which are going to act as the barriers, covers, and protective layers. I have shown it over here in the brown color. These engineered backfills are nothing but especially designed geomaterials, which can be compacted and which would be able to sustain the type of thermal stresses which are going to act on them, the type of radioactive attributes of the waste which they might get exposed to, and so on. So this itself is a research topic. The third one is, having disposed the waste units, how are you going to close these systems or repositories? And what type of monitoring should be done so that nothing untoward happens to the environment? So this is what is known as post-closure response. Most of the atomic units of the countries are looking for these type of help from the geoenvironmental engineering professionals. Then comes the modeling and monitoring methodologies. How would you make sure that despite taking all these precautions, nothing is leaching out, nothing is moving out of these units into the groundwater? So this is where the best way would be to model it mathematically and to monitor by using different techniques and to show that nothing untoward is happening. So this type of situations are very, very hot topics right now, where people are talking about thermo-hydro mechanical coupling, because the thermal effects come due to the attributes of the waste. Radioactive waste will have higher temperatures, 200 to 300 degrees centigrade, lasting for several years. Hydro, movement of water. Then mechanical stresses, thermal stresses, it could be mechanical stresses, and then chemical species. All these wastes would have some chemical species. So this becomes a very good case for THMC modeling, which several people have done. Please refer to the work done by them. Our group has also done some studies. Now, many times this THMC also adds on to it the biological component. So this becomes THMCB. And I'll be talking about this influence of biogeo interface slightly later, where you will get a feel that why this type of biological coupling is required. Most of the geomaterials are not devoid of microbes, bacteria. And this gives an added advantage in creating a system which becomes very, very impervious. Up to a certain limit, you can compact the soil mass. But suppose if I want to make a system where no water can either ingress into it or no gases can come out of it, I would like to take help of the biological activity, microbial activity, to seal the pores. Unfortunately, these type of situations, the way they've been handled, there are a lot of assumptions and limitations. So this is what actually I was referring to in my title of the talk, the limitations and possibilities, like what can be done. Now, what can be done will be answered once you have understood what are the limitations and what are the assumptions which have gone wrong and accidents have occurred or the failures have occurred. So the first culprit is the assumption that these geomaterials are isotropic and homogeneous in nature, which we understand is not a very valid assumption. We have also assumed that most of these soils are inert, which is not correct. Inert, when I say, they are devoid of physical, chemical, thermal, electrical, biological alterations or weathering. Now, alterations in properties and weathering is always going to be a function of time under different types of environmental conditions. So assuming that the soil mass or the geomaterials like rocks are passive is not a very good idea. Another one is presence of the organic matter, which plays a very big role in degradation of its own over a period of time. So though its effects are very, very well known, this has been ignored, which should be considered. We have also ignored very conveniently the mineralogical alterations which occur because of the extreme conditions in which the geomaterial might be. Dr. Cole is here, and his thesis was on hydrothermal activation of fly ash. So fly ash is a quartz material. When it is acted upon by hydroxides, we call it as alkali activation. At very high temperature and pressure, a different type of minerals get formed. Now this process goes on in nature. And because of this, the material loses its basic characteristics. Now, whether it is going to be good or bad, both aspects are there. We call this process as zeolitization. I'll be talking about this. Now, once the mineralogical alteration occurs, the geomechanical characteristics will also change. So please refer to the papers which were written by Dr. Kole, my other student, Bhagwanji Jha, Dr. Naveen Koshi, and we have done synthesis of these zeolites, and we have utilized these zeolites as a molecular sieve for treatment of wastewater and sludge. You will realize that this is one of the best possible applications of the industrial waste. By giving it a bit of treatment, we can alter its state and we can make it more active. So most of the time, we have not considered the temperature, pressure, and humidity, which are acting on the geomaterials and which are responsible for changing its overall properties. We have also not talked about the phase change phenomena, how the phase of the material changes. Now, when I say phase change, this could be new phase formation also, or whatever phases of the liquid, gas, and solids which are existing in the material might also change because of pressure, temperature, bioactivity, and humidity. So now everybody is realizing that this issue cannot be ignored. All right. So how soil grains might get changed because of the limitations and assumptions which I have discussed over here, how ice crystals get formed, phase change, what happens to the water in the pores, what happens to the leachates which are present as a pore solution, what happens to the free gases which are present in the geomaterials, what happens to the trapped gases. Now, trapping of the gas could be because of very high pressure and at low temperature. I'll be discussing about this. Similarly, a good example would be frozen and unfrozen water which is present in the soil mass. Now, all these things are now coming in the realm of environmental geotechnology. So there is a very big scope for doing fundamental research and taking all this research to the field. And you can help your different organizations, government agencies, industries for their overall development, keeping in view the environmental changes which are occurring and how to overcome them and how to get rid of the disasters which are happening because of the ignorance or the poor assumptions which we have made or because of the limitations of our thoughts. So these complexities were realized and people started talking about, response of geomaterials to thermoelectromagnetic fields. And I'm sure some of you must have come across how the thermal properties, electrical properties, magnetic properties of geomaterials, influence its overall characteristics. So some of my students who work in this area, particularly those who are working on sensing techniques for moisture content and for underground cable operation, the laying operation, design of fluidized thermal beds, where thermal properties of the material becomes very, very important. This is where people also started talking about heat and moisture migration in the soils because of thermal effects, electrical effects. So this also led to the soil remediation through thermal and electrokinetic techniques. And I'm sure you must have come across the cracking characteristics of soil. So the cracking happens once the excess thermal stresses act on the geomaterials. In radioactive industry or the nuclear waste disposal industry, uh, normally people talk about cracking of the host rocks. The temperatures could be so high and the thermal stresses which are building up might be so high that the entire rock mass may crack. So this is going to be an eventuality which has to be taken care of. I hope you realize that these small words which I have put together over here have very, very big implications, and they have to be studied properly. So I'm sure that those of you are interested in doing research, there is a big spectrum of topics which you can select and you can work. Then what happened? This was an interesting transformation. Geomaterials, a journey from marginal to mainstream materials. That is the development of economically viable and sustainable infrastructure and other applications. Geomaterials, soils, rocks are becoming scarce. Now the question is how to go ahead with the development, infrastructure, other applications, and so on. In short, when geomaterials do not have desired characteristics like clays, peats, organic soils, now what you are going to do? You can't stop the project. So that means when mainstream natural resources are not available, what we have to do? We have to alter them. We have to augment the properties. So many researchers have done research related to augmentation, enhancement of geotechnical properties. All right. By adding different types of additives, by exposing the material to different types of thermal effects, like making a brick is a good example. You take the clay, if it is non-organic material, add some chemicals to it, and then fire it, and it becomes strong. So this is one of the augmentation techniques or enhancement of the geotechnical properties which we are talking about. Immobilization of contaminants. The materials have been utilized to immobilize so that the contaminants do not go out of the matrix of the waste and they remain confined. So these type of studies have been done. Cementitious materials have been utilized for soil stabilization and particularly remediation of soil erosion and cracking by adding some materials which are truly speaking marginal materials, like the most of the time the waste materials which are coming out of the industries. So this was also a very interesting transformation in thinking of the researchers, and they have contributed a lot. Another interesting twist which I find in our profession is from abiotic to biotic. Good examples are precipitation of cementitious product in marine and humid environment. We call it as MICP, microbially induced calcite precipitation. Decomposition of peaty soils. Then biogenic methane emissions from landfills or marine sediments. I will give you some examples regarding where these issues are becoming very, very critical in today's world when we are facing a acute energy shortage. Then, of course, nature-driven erosion control and bioremediation mechanisms. This has led to many of us to work on bio-geo-interface. Truly speaking, you are using bio species. It could be microbe, it could be bacteria for remediation of contaminated geomaterials. I can also use phytoremediation techniques by planting trees and then forming a root soil interface. root soil environment interface, which is a very, very hot topic for doing research. Biomineralization of geomaterials. By using bacteria, if I can coalesce the particles, sands, in deserts. Suppose if I have to rehabilitate the deserts, this seems to be a good technique. Unfortunately, these studies have not been taken up to the real life situations, which is going to be a big challenge. Then immobilization of contaminants through calcite precipitation. When the calcite gets precipitated in the pores, the durability increases, and this is a concept which is being used in bioconcrete. The same concept can be utilized in soils also, where we can precipitate calcite to choke the pores. Now, choking of the pores is not going to allow, any leachate which gets formed because of degradation over a period of time due to the environmental conditions out of the matrix of the waste or out of the immobilized matrix of the waste. So these are very, very challenging topics, which can be taken up by researchers. There are situations where I would like to decompose the material faster. Municipal solid waste. Krishna is a champion. He has done a lot of work. All right. So many researchers have been doing research in municipal solid waste, sludges. These landfills are not made to store the waste. They were basically created to cook them quickly, decompose them so that the volume reduction takes place and you can accept the next batch of the waste. Unfortunately, this is not happening. So I can utilize these type of concepts, biogeointerface, to accelerate the decomposition process of the municipal solid waste and the sludges. Biocovers for landfill gas emission mitigation. I'm sure you'll find several papers, a very hot topic right now where people are contributing. Biofilters, geomaterials acting as biofilters so that the landfill gases do not get emitted into the environment. If you go to the webpage of Professor Krishna Reddy, you will find he has published so many papers on simulating how to trap these gases, how to create the landfill covers, which will not only stop the ingress of water, but they will also stop the exgress of the gases which are getting created because of decomposition process. So these are very interesting thoughts. And of course, the gaseous soils. So I am skeptical about this biogeo interface. I guided several PhDs and masters, and Dr. Shashank was the champion who did a lot of work from a laboratory. Here I am showing you some of the photographs, SEM images of soils which have microbial activity in it. So these microbes do a lot of tricks, provided they get nutrition. Water could also be nutrition. All right. So truly speaking, this has proven the fact that soil is not a lifeless entity, which we had been assuming to be, and which was a great injustice done to the soil mass. The moment nutrition is provided, the moment water is provided, these become hyperactive and they may do damage to the soil structure, or they may upgrade the soil structure also. Both ways it is possible. Upgradation would be MICP, and degradation could be bio-induced degradation of the material. We did atomic force microscopy also to show the mechanism of how MICP occurs on the sand grains. Now, this is very important to understand in today's context, where you will find several papers being published by the researchers without realizing what are the challenges associated with biogeo interface. All right. One thing is doing these experiments in the laboratory in a controlled environment on a controlled material, which now has less significance. Enough research has been done. Now, this concept has to be taken to the field, particularly in one of the consulting projects where I was working on stopping the seepage of water in the mines for excessive deep mine creation. One of the questions and the challenges which I threw to the researchers was, can you do MICP up to 40-45 meter depth to stop seepage of water in the deep mines? So these are the challenges which one has to take. Time has come when these studies should be taken to the real life situations. What are the challenges? The challenges are field scale implementation of biocementation and to establish the effect of microbial products such as biofilms and EPS on the coarse-grained geomaterials. So Dr. Shashank studied these thoughts very carefully, and he has done AFM to show how on the coarse-grained material the bacteria sits, deposits MICP, and subsequently and sequentially how further MICP layer gets formed on bacteria itself. So here we have used the concept of AFM to compute the energy associated with each type of bonding which is occurring between the MICP and the sand grains and the bacteria and the MICP itself. So these fundamental research should be useful in guiding researchers properly. A lot of scope of research is there. The material changes, the type of microbe changes, the type of bacteria changes, the whole context changes. The environmental conditions change, the entire findings will change. So a lot of scope to do work, but my request is please consider the practical aspects. Another big challenge is the same mechanisms which are going to happen in the fine-grained soils. Now, when you talk about fine-grained soils, I am sure you will realize that biosuction becomes a very important parameter. How this biosuction can be controlled, how this biosuction will help us in understanding the fundamental properties of the fine-grained materials. So this is where the new perspective came regarding the suction, that total suction is not only the addition of metric suction and osmotic suction, which has been otherwise considered. This should also be including biosuction due to the microbial activity. And subsequently, what I learned from my students over the years is this series is still incomplete unless you add cryosuction to it. Because when the formation of ice occurs, this is a process where withdrawal of the moisture is taking place from the geomaterials, which is equivalent to the drying process of soils. Withdrawal of moisture is bound to produce suction. This is what is cryosuction. So those of you who are working in this area of suction measurement, my request would be that please consider all these four components and go ahead. Very hot topic, I would say. And as far as I am concerned, I do not know much about it, but these are my questions, and I think that somebody will take this as a challenge and work on it. Further came the sustainable man-made geomaterials. This is something which is very revolutionary, very contemporary, where all sorts of waste, which I was talking about, industrial byproducts, they can be utilized, they can be valorized. Valorization is creation of value. For me, nothing is a waste. So the idea is if I can use this material and if I can create some synergy with the geomaterials, that would be a win-win situation. So I can use this material for waste disposal, storage facilities, land reclamation, sustainability. These are the new terms which are getting added up to our subject, environmental geotechnology. Because a few years back, sustainability was there, but we never talked about creating a marketplace for the man-made material, man-made resources. But now the time has come where several technology transfer startups should be done for treating the waste as a valued material. So there should be a marketplace. People should be able to buy it, sell it, and create man-made materials out of it. Circular economy also gets added up to this. I was leading this mission, industrial byproducts, on behalf of Indian National Academy of Engineering, New Delhi. You can visit my site and you can see the details of how much we could succeed in that and what a lot has to be done in this context. So this is where actually this thought comes to mind that we should be having waste to welfare mission also by utilizing these geomaterials, which are not a waste. By using this concept, several people and my own students have utilized industrial byproducts for soil and rock mass stabilization and replacements of conventional geomaterial for infrastructure development. My student Pratvendra Singh is working on waste rubber, landfill mine residues. Mr. Goli is working on that. Then we are trying to create different types of composites out of this successfully. We have done it, in fact. That was a part of Goli, resource recovery through landfill mining and urban mining. And these composites we are trying to use as a neo geomaterial or man-made geomaterial. We can also use these materials for removal of contaminants by enhancing their inherent properties. And then they will become very good sorbents. This is a good example of what I was talking about. LFMSF is the landfill mine soil-like fraction. Once you do mining of the landfill, whatever is remaining becomes LFMSF. And industrial byproducts I can utilize to create composites by using the recycled plastic. So it's a simple concept. The way you create typical composites, cement, concrete is also a composite. What we are trying to create is the neo composites, where the binder happens to be the waste which is coming out of the landfill plastics. And fillers are also coming out of the landfill in the form of biomined material and industrial byproducts. So this work has been successfully done by Goli, and there are several advantages of doing this. It's a complete solution for waste management. Utilization of both municipal solid waste and industrial byproducts, and no leaching issues will be associated with this. But the question is whether it is so easy or not. The answer is not really so easy. You have to have good knowledge of polymer science and the science of interfaces to create a beautiful composite which is going to be useful for the mankind. A lot of scope for research, consultancy, and startups you can see coming out of this idea. One of my students, Mr. Pratvendra, is working on waste rub in rubberized concrete and composites. So the concept is simple. I can replace the fine and coarse aggregates, naturally occurring aggregates, by rubber. And I would like to see what type of concrete has been created, how durable it would be, what would be the applications. And similar concept can be utilized by encasing the waste rubber particles with the polymer coating. So these type of, you must be realizing that environmental geotechnology is also entering too much into the materials, the man-made materials, the material which were not having any value earlier. And this is a major shift, I would say. Another major shift which we observed in our subject is energy and reversal of climate change, which I would say is a very, very major shift in the recent times. So everybody is dependent upon the fossil fuel right now. The whole idea is to reduce it and exploit the green energy sources or the renewable energy sources, unconventional energy sources. And this is I was talking about the marine and permafrost regions where the methane which is present gives you an opportunity to, in the form of gas hydrates, which I am now going to talk about. And the big challenge would be how to tap or harness the energy from the hydrates. Another thought which we are working on right now is how to harness the geothermal energy. And I will be discussing it a bit in detail. If you follow all these things, these type of concepts, greenhouse gases concentration can be reduced in the atmosphere, and we can bring it back to pre-industrial revolution era. This is nothing but the net zero effect. So one of the initiatives which was taken by my ex-student, Dr. Lijit, was formation of methane gas hydrates bearing sediments. We did synthesis in the laboratory, what happens in offshore environment at several hundreds of meters of depth in the seabed. Extreme pressure temperature conditions, the methane gas, which is biogenic or thermogenic. Biogenic is because of the bacterial activity, thermogenic is because of the temperature. It gets trapped in the pore solution and it freezes. It forms the hydrate crystals. So this is the research which was done by Dr. Lijit and Dr. Sayyam and one of my students, Dr. Jeevan Joseph. These are the guys who have really done wonderful work. And now we are trying to work on methane CO2 replacement. That means in hydrate-bearing sediments, if I dissociate them by manipulating pressure and temperature, and if I inject CO2, can I liberate CH4? I'll be talking about this. The second is storage of carbon dioxide in deep saline aquifers, which is a part of carbon capture storage and carbon capture utilization and storage. Then extraction of geothermal energy from abandoned oil, gas and well. The question is the oil and wells which are becoming non-productive. They are about to be abandoned. That means there is no yield. What should be done with them? Can we use them as the powerhouse? Answer is yes. What is the risk associated with geological carbon sequestration? And what is the impact of wild forest fires on soil properties? Catastrophic. I think you are hearing what's happening in some parts of the world where the temperatures have risen too much, and then which is resulting in a big hazard in terms of forest fire. Arvind is here. He has championed one paper on wild and forest fire and what are its implications and how these type of situations are leading to the change in soil properties. All right, how the soil properties are going to change, how the vegetation cover is going to get altered, and because of this, soil erosion is taking place. The land is becoming barren, and so on, and landslides might occur, whatever. Just to give you a glimpse of, in the realm of energy geotechnics, what we are doing at IIT Bombay, and I am very proud to be associated with my research group here, who has taken this such a challenging task. So environmental geotechnology is now converging too much into energy geotechnics. And I'm going to show you what are the challenges which we have as researchers and how to fulfill them and how to work on them. These are the topics on which we are working. Synthesis of CH4 and CO2 hydrates inside the laboratory. Similar thing happens in nature. So we are emulating nature in our laboratory at very high pressure, low temperature by using methane gas and carbon dioxide. And intention is to release CH4, which is trapped over there, by injecting CO2. So this becomes another topic which is being pursued by my research scholar, Mr. Reddy Srinivas Rao. And then CO2 enhanced oil recovery. When you have heavy oil, can I inject CO2 to make it light oil, flowable, and then I can collect it. Geothermal energy, where we are trying to use water and carbon dioxide as working fluid, and this is being done by my student, Ms. Fakra. And CCU in industrial byproduct, where Mr. Kamran is working on the philosophy that hyperactive soils, if I can neutralize them, if I can mineralize them, all right, this would be a very good theme. So some of the industrial wastes which are coming out are having extreme pH values, highly basic, highly acidic. So those which are basic if I can utilize CO2, carbon dioxide, I can say CCU, carbon capture utilization, for neutralization of the byproducts. And then my another team members are working on topics like geological storage of CO2 in saline aquifers, which is a good example of carbon capture storage and carbon capture utilization and storage. So these are topics which are being pursued by Yogendran and Singh Manohar. I'll just give you a brief idea about what are the challenges associated with these topics and where geotechnologists should take them up in creating the micromechanical models. And of course, those who are experts in earthquake engineering would also be, getting benefited from these thoughts. And the time has come when everybody should collaborate. So the energy geotechnics basically harps upon the multiphase system. Multiphase system means this is a typical pressure temperature curve for a gas. And now I think you can realize for the first time we are using the term soil, water plus ice. In the low temperature, the water freezes, ice formation occurs. And as I was been telling, that because of decomposition of the organic matter in the soil mass, the gases are getting produced. And these gases might get trapped in the water molecules. In the pore solution, hydrate formation occurs. And sometimes the entire gas may get eaten up by the pore solution to form soil, water, and methane gas system. So this is a very conceptual model which we created for understanding the geomechanical characteristics of hydrate-bearing sediments. When I say geomechanical, these are basically permeability, deformation characteristic, elastic modulus, Poisson's ratio, gas permeability, hydraulic conductivity, their collapsibility, shear strength parameters, and all. So this is a very different state of the material, which requires a good understanding for our harnessing the CH4 methane gas from the sediments. When I talk about CH4 CO2 replacement, this is again a micromechanical model. This is the hydrate setup where you have sediments, where you have methane hydrates. And suppose if I inject CO2, we have carbon dioxide plus water freely available. Now what's going to happen? This system is going to get formed. We are going to have CO2 hydrates and methane gas is going to get liberated. So this is the whole idea about CH4 CO2 replacement. It's too early for us to speak this in the scientific forum, because I hope you will realize that these are very, very complicated systems and we are trying our best to understand them, learn from others, and then make things very simplified. This type of philosophy is going to be very useful for CO2 storage, and which is going to fulfill our requirement of net zero. I hope you can realize this. Then the question comes that what to do with the abandoned oil and gas wells. There are several oil and gas wells, which are posing a major problem. You can't leave the oil wells unattended, unfilled, unclosed. So what should be done? This is where the thought comes that if you just leave them like this, methane will leak through it. It will cause several problems to the Geoenvironment. So what should be done? We can create wells of opportunity out of it. We can do retrofitting of abandoned oil and gas wells. Retrofitting means I can inject through some proper paraphernalia some fluid inside, and I can utilize the heat which is associated with the rock mass. From where this heat is coming? This heat is coming from the mantle of the earth. And normally we have seen the typical temperature ranges would be 150 degree, 160 degree, and so on. It's a very good temperature where if I inject some fluid, the fluid will interact with the hot geomaterial, the reservoir rock, and then I can collect it from some other site as a production well, or I can suck out the fluid. And this heated fluid can be utilized to produce electricity, air conditioning, sustainable development. So Fakra is working on this topic, and we are trying to tie up with some industries who are interested in this type of philosophy. So the possibilities and role of environmental geotechnology in this subject would be basically heat and mass transfer through porous media. You are injecting a fluid at a normal temperature, it goes inside, and what happens to this fluid? It might undergo a phase change. If the temperatures are very high, a steam gets formed, and then you can use it for running the turbine. Another question is, how would you establish the geomechanical behavior of rocks at higher temperatures and pressures? Remember, these wells could be as deep as 2.5 kilometers to 3 kilometers, oil and gas wells, all right? So how I'm going to reinstate these wells as a energy powerhouse is a big question. What type of fluid should be utilized? Whether CO2 can be utilized or not to attain net zero through carbon sequestration. This would be something very, very interesting to work on. So pore scale interactions, when we talk about the geological storage, it's very challenging topic on which we have recently started working through my students, Singh Manohar and Yogendran, and hope you will realize that the whole idea is to inject CO2 either in the gaseous form or in the subcritical form into the reservoir rock, which is saturated with brine. Now, this is the initiative which has been taken, keeping in view that most of the political leaders are committing that by 2030, 2050, 2070, we'll be having a net zero situation. But the process is very, very complicated if you look into the microscopic view of at the particulate level. You know, the CO2 might get structurally trapped or dissolved in the pore fluids. How are you going to model this? It's a big challenge right now. So typically these are very high pressures, and because CO2, if it is subcritical, temperatures are going to be quite low. How this interaction is going to occur, how these zones are going to get formed, how to model these zones, where I should be purging the CO2 gas, and whether it will be effective to up to what distance. Remember PVDs, which you have designed, the wells which you use for extracting the water, and so on. So this is also a multi-phase porous media. I am not going into much details of this. Very soon you will be getting some papers to read. But those of you who are really interested can start doing the groundwork, and you will realize that a lot of physics is involved into this. A lot of cryogenic studies have to be done. Phase transformation of the fluids and the material has to be studied, and so on. At the same time, how petrophysical properties and geomechanical properties of the reservoir rocks are going to change. This is what is to be studied. There is a risk associated with this whole process, and this is what is being studied by Singh, my student. When you are injecting CO2, the chances are that the faults may get activated. There could be induced seismicity. There could be leakage of carbon dioxide in the water bodies. The well-bore instability might occur because the rock is getting dissoluted. And there could be dissolution of the cap rock also. Now, this subject is quite interfacing with engineering, geology, petrophysics, and so on, where we are talking about, what would be the state of material if it gets altered. So fault activation could be, in simple geomechanics terms, when you are injecting gas, the pore pressures will go up, effective stresses will decrease. And when effective stresses will decrease, the material will lose its strength. And then the opening of the fault may occur. So if I am injecting CO2 over here, the chances are the whole thing may find out an easy escape route from the opened up fault. Some of you must be aware of that some of these ideas I have covered in my book, Environmental Geotechnology, Meeting Challenges Through Needs-Based Instrumentation, where these topics have been studied and included in my book. And those of you who want to learn this subject, I would suggest that if possible, you can you can access this book and go through it. There are several talks and my video recorded lectures on my web page, and I offer this course also at IIT Bombay, which can be visited. So I think, Krishna, now I will cut short because I think for the sake of time, what do you say? How much time I have?
Yeah, go ahead. Just wrap it up if you can in some 5 minutes.
So, yeah, so most of the work which we are doing is related to the SDGs, and the way forward. I have given a big series here. What needs to be done? New materials, emerging contaminants, fire and its influence on the geomaterial properties. Uh, this is going to be very, very challenging work because most of the world is facing this type of fires. Be Canada, be it Greece, um, uh, even I'm sure France is also having tough time. Australia is having the problems. So every continent, every country is having these problems. IoT utilization, AI, ML, coupled phenomena has to be studied. What I was discussing here for different applications, particularly for energy geotechnics. Bio-geointerface has several questions rather than the solutions. And I think the future generation will take care of it. And of course, renovation of monuments and old structures, which is also becoming a part of our subject or maybe our profession. Pandemic. I think we should also consider this. The pandemic, disaster, destruction management are becoming a major part of environmental geotechnology, I would say. During the COVID time, environmental geotechnics came out with several themed issues, and we tried to educate the world at what's happening. Similarly, in mining activity, we are seeing a very clear role of environmental geotechnologist. How to do the entire mining process in the best possible, following the environmental norms and constraints. So, infrastructure on challenging geomaterials and deposits, Arctic region, lunar, Martian, land creation, dealing with organic soils, and so on. To sum up everything, what comes to my mind is that there is a major shift, what has happened in the realm of geotechnical engineering, I would say, for the time being. Tens of meters of geospace has got changed to several thousands of meters. So earlier we used to talk about excavations, pavements, building foundations, pipes, ducts, tunnels, soil stabilization, which was conventional geotechnical engineering. Space was up to minus 50 meters. But look at the current situation. I mean, we have gone up to almost minus 3 kilometers. And this is where the environmental geotechnology finds its utility. Okay. Waste from industries, municipalities, landfill, industrial waste disposal, utilization of the waste product, contaminant transport, unsaturated soil formation, dress sediments, cut-off walls, trenches, permeable reactive barriers, ultra-deep mining, high-level nuclear waste disposal, gas hydrate bearing sediments, geothermal energy, EOR, carbon capture utilization storage. So this is what I thought of sharing with all of you, those of you who keep asking, what is the scope for the subject? I mean, scope is tremendous, I think.
Yeah.
In our lifetime, we cannot do study and follow all this. So this is where I just wanted to bring to your notice about the Shah project, which I am leading on behalf of the Department of Science and Technology. This is a consortium project related to carbon capture, utilization, and storage. We are trying to study, in some of the parts of the Indian reservoirs, that if I inject CO2, what would happen? And this is under the auspices of ACT, Accelerating Carbon Technologies. And this is a project which is funded by Norwegian Research Council. And NGI is the leader, and all of us are working together. The whole idea is to do more capacity building, create more workshops, exchange of students, professionals, knowledge base. You can visit web page, and you can also follow the activities of Sharp at Sharp CO2. Thank you very much. So by the time I was making my slides yesterday, what happened? Everybody knows. And this is the ever-evolving subject. I thought that I'm going to confine my discussion only up to the Earth. But look at that, what has happened yesterday. Chandrayaan has been a success. Now this is going to create expand the realm of the environmental geotechnology. And in my opinion, in the days to come, you will find some colleagues working on lunar environmentology. Krishna, how did you find this word?
It's good.
So,
You are creative.
so those who say that there is no scope, I think
Yeah.
they should follow it. Every minute the slides change, every minute our thoughts change. The whole nation was watching yesterday the soft landing of Chandrayaan on the South Pole of Moon. And then this thought came to my mind that, see, we are trying to wind up the subject. Truly speaking, a new subject is about to start. And so this is the legacy which we are going to leave behind for our the young generations. So this is the famous quote which I believe in. If you are constantly facing new situations, it means you are living a life of growth and great possibilities. So please do not think about that there is no possibility, there are no opportunities. Just bury these questions. Yes, now from my point of view, I'll be very happy if you can suggest the way forward for myself, my research team. Your questions would help us. Your questions could be a guide for us, and they will definitely help us in our endeavors. Thank you very much for your kind attention. And Krishna, once again, thank you very much for giving me an opportunity to open up my thoughts in front of the public and, sharing them with the generations who might do wonders in the days to come. Thanks.
Yeah, thank you. Thank you so much, Dr. Singh, for your excellent presentation. I think, one of the